Chapter 10 taught you how to do a t-test for comparing average scores or comparing mean scores for two samples when these samples were unrelated to one another, when people in one sample were not related to the people in the other sample. We call that an independent samples t-test. Chapter 11 is called a related samples t-test, but it's also another term for it is a dependent samples t-test, to make a distinction between the type of t-test you did in Chapter 10 and the type of t-test you'll be doing in Chapter 11. In Chapter 11, we're using dependent samples t-test or a related samples t-test. So make sure that as you're reading Chapter 11, you understand the difference between the procedures and the purpose for the t-test in Chapter 11 versus the purpose and the procedures for the t-test that you did in Chapter 10. There are similarities and there are differences, and the similarities can be confusing. There are many occasions where we have a sample of people and we measure that sample twice, or we put that same sample through different treatment conditions, and we want to see whether there is a change between the first measurement and the second measurement, or a change in the group between the first condition and the second condition. But we have one group and we treat them or measure them differently. We might want to know whether attitudes change after people have a particular experience or see a particular video. British Petroleum has produced an infomercial which is trying to change people's attitudes towards it. They feel that when we had the massive oil spill or oil leakage in the Gulf, people felt badly about British Petroleum. So now you'll see an infomercial on TV related to British Petroleum. We could pre-test people about their attitudes towards BP, post-test them after they've seen the video, and see whether those attitudes have changed. That would be an example of where we would do a related samples or dependent samples t-test. So there is the hallmark for this kind of test is a single group of individuals, and there are two scores for each individual in that group. In this kind of research, we have hypotheses that there will be a difference from one measurement to the next measurement, or a difference between two treatment conditions for the same group. Our null hypothesis would be that there is no difference in the measurements, or there is no difference in the treatments, and our alternative hypothesis would be that there is. So for each person in the group, we compute a different score. We designate one group as the second group, another group as the first group, and we compute a different score by subtracting the scores in the first measurement or in the first treatment condition from the scores in the second treatment condition for each individual. The term related samples means not so much that the people in the samples are related, though it can mean that, as what it really means is that the scores are related. Pre-test and post-test scores for the same people are related in some way. They're dependent in some way. Another term, as we said, another term for the related samples t-test is dependent samples. One set of scores is dependent on the other set of scores. But another term, it's also called a matched subjects design, where you would have people in one treatment who are matched with people in a second treatment. Your book gives you examples of that. But those types of research designs are rare, and in this chapter, most of the examples that we give will be with related samples and not matched subjects designs. We'll be talking about one group and two scores for each person in that group. When you have a matched subjects design, you have two groups of people, but the people were selected in the groups because they're similar in some way to one another. we treat those as if they're identical. And we'll have a score for the people in one group and a score for their match in the second group. And we compute a different score between the matched subjects. So if in one group we had a 15-year-old male, and in the second group that person was matched also with a 15-year-old male, we would subtract one person's score from the other to see if there is a difference between those matched subjects' scores. But match designs are hard to use. They're hard to develop. It's hard to often find a matched subject. In this chapter, we'll primarily be using repeated measures designs, where we take the same group of individuals who are in both treatments, we measure them and look for differences in the pairs of scores for the same people, not pairs of scores for related people. So most of the examples, just about all of the examples in this chapter, and on the test that we take in this class will all be with repeated measures for dependent samples or related samples. We won't be studying examples of matched subjects designs. Repeated measures tests have hypotheses. The hypothesis is that the two treatments that the same group of people experienced, there really isn't any difference between them. So when you measure the same group after each treatment, your mean difference, when we subtract the scores from one treatment from the scores in the other for the same people, that the difference will be zero. That's our null hypothesis, that the treatments really aren't the same or they didn't have any effect. If we were pre- and post-testing people, we would say there's no difference between the post-test scores and the pre-test scores. The attitudes didn't change, for example, between pre-test and post-test. We have a theoretical population in which our null hypothesis is saying that the difference between the pre-test and the post-test, or the difference in the measurements in the two conditions, there is no difference, it's zero. And we have an alternative hypothesis that the population differences are different from zero. It says greater than zero, but it could be, think of this sign here as meaning different from zero, and not so much greater than zero, just different from zero, because scores could have gone up and scores could have gone down. In both cases, they'll be different from zero. Here we have an example of where we have a population of different scores. A group of people were measured before and after, or after one type of treatment and another after one dosage level of a drug, and then they were measured after a second dosage level. And we have this population of different scores. And our null hypothesis is that the mean difference is zero. Our alternative hypothesis is that it's something different than zero. If you look at the table here, you can see that there are 4 subjects. Each subject is measured twice. We have x2 and we have x1. And if we subtract x2 from x1, we have a different score of 4. Here we have a difference of -2, 13 minus 15. Here we have a difference of 3. Here we have a difference of 1. These are our different scores. And what we want to know is when you average out these different scores, would that average difference be 0, or would it be something different from 0? In this case, if we were to add these scores, we would have 4 plus 3 is 7, plus 1 is 8, minus 2 is 6. So the sum of the different scores would equal 6, and the mean difference would be 6 divided by 4, which would be 1.5, would be our mean difference. We'll give more examples of these, but that's basically the way the data are collected, the way the data are set up, and the way the differences are computed. So your null hypothesis is saying that there is no consistent or systematic difference between the two treatment conditions. The population parameter of different scores will equal 0. In the previous chapter, we had our null hypothesis was that the mean of group 1 minus the mean of group 2 equals 0. Well, here we only have one group, and we have a group of different scores, and so where's null hypothesis written, the mean difference, the population of different scores, is 0. It doesn't state that each individual will have a different score equal to 0. The scores could have increased. The scores could have dropped. It just says that the scores will be different. And that when you add up all these differences and take the mean of all these differences, that the mean difference will be 0, not that any person's individual score is 0. And as it says here, some individuals show a positive change from one treatment to the other, and some will show a negative change. People could have improved their attitudes after viewing a film about British Petroleum, or they could have actually felt worse after viewing a film about British Petroleum. But on the average, the entire population will show a mean difference of 0. This is the null hypothesis. On the average, the entire population will show a mean difference equal to 0. This mean difference could be something different than 0. It could be a mean difference of 1, or a mean difference of 2, or a mean difference of a pound, or a mean difference of a certain thickness if you're producing some kind of product. But is this difference due to sampling error, or is this difference because of the treatment that these products or the people were put through are really different? And so we have the same concept of sampling error. You're going to see different scores that are different from 0, but are they different enough from 0 that these differences are due to the treatments or the measurements, and they're not due to sampling error? Our alternative hypothesis is that the mean differences between the two treatment conditions, or the mean differences between the two measurements, does not equal 0. The alternative hypothesis in chapter 10 was that when we subtracted the mean of one group from the mean of another group, we did not get 0. But in chapter 10, we had two groups. Now we have one group, which is why we have the mean difference. We don't have two samples, we have one sample, but we have different scores for that sample. And the repeated measures t-statistics forms a ratio, just as the independent samples t-statistic formed a ratio. In this case, that we'll be doing t-tests. We'll only do t-tests with the repeated measures research design. The t-value that you compute, the t-statistic that you compute, will be computed by finding the mean difference between the two conditions or the two measurements and dividing it by the standard error of the mean difference. When you're doing this type of research, you have to compute the mean difference. We'll give you an example in a minute. And then you have to compute the standard error of the mean difference. And that standard error of the mean difference will be the standard deviation of the different scores divided by the square root of the sample size. So the numerator measures the difference between the sample mean and the hypothesized population mean. Your formula then says find the mean difference, subtract the population of mean differences from that, and divide by the standard deviation of the mean differences. This will be 0, so in effect we shorten the formula to say mean difference over the standard deviation of the mean differences, and that gives you your t-value. Just as in the previous chapter, we had the mean of group 1 minus the mean of group 2 minus the population parameter of group 1 minus the population parameter for group 2, but we said this will be 0 under the null hypothesis, so the formula, the numerator of the formula only included mean 1 minus mean 2. This formula works exactly the same way. Here, degrees of freedom is n minus 1, only n equals the number of pairs of scores. Not the number of scores, but the number of pairs of scores, and that's an important distinction, so as you read the chapter, make sure that you understand that n here is referring to the pairs of scores. If we have 10 subjects, we'll have 20 scores, but we have 10 pairs. So the degrees of freedom would be 10 minus 1, which would equal 9. And all our calculations are done with difference scores. I'll show you an example of that. To get the standard error of the mean differences, we're going to find that we calculate the variance of the difference scores, and again it's the variance of difference scores divided by the sample size, or we take the standard deviation of the different scores and divide it by the square root of n. There should be a square root here. So the standard error, and this is standard error of the mean difference, would be the standard deviation. This would be the standard deviation of the difference scores divided by the square root of the sample size. So here we have an example of a repeated measures problem. We'll use products instead of people just to show you that this type of design can be used in business, this type of design can be used in education, this type of design can be used in medicine, where we have one group and that group gets 2 interventions or 2 different measurements. So here we have accounting procedures. One type of accounting procedure is called first in, first out. Where inventory comes in and we evaluate inventory costs based on first in, first out, or last in, last out. So we have these 2 types of ways of keeping track of inventory. And there are different costs for these procedures. We have 5 products, and the cost in millions of dollars for when we do inventory by the first in, first out method was $225 million. And for that same product, when we use the last in, last out accounting method, the cost was $221 million. For the second product, the costs were $119 million versus $100 million. For the third product, $100 million, and for the last in, last out accounting method was $113 million. So you'll notice we have 2 measurements for each product. For product number 4, under one method of accounting, it cost $212 million. Under another method, $200. And finally, for the 5th product, under one method, it was $248 million. And under the other last in, last out method, $245 million. And then our question is, were there any differences in the costs depending on whether you're using a first in, first out or a last in, last out method? Our null hypothesis is that the mean of these difference scores is going to equal 0. Well, what difference scores are we talking about? Well, here we have x2, and we'll call the first in, first out scores x1. I'm sorry, x1. And if we subtract x1 from x2. We have 221 minus 225. This gives us minus $4 million as our difference score. It costs $4 million less under the last in, last out method of inventory. For the second product, it cost $19 million less. The third product, it cost $13 million more. It's important to keep track of signs here, as I'll show in a minute. Our fourth product cost $12 million less, was $12 million cheaper to do it under the last in, last out method. And our fifth product was $3 million cheaper under the last in, last out method. So we have different scores. Notice as these different scores aren't zero, but there is somehow there is a difference in the cost between one method and the other method. And what we want to know is, what is the mean of these different scores? So to find the mean of the different scores, we would add up all these differences, and you would get a sum of the differences would equal 9 plus 14, 23, plus 12 is minus 35, minus 3 is minus 38, plus 13 would give you minus 25, and we divide that by 5, and we get a mean difference equal to negative 5. Is this mean difference large enough for us to say that there is a difference in the cost between the two methods, or is that negative 5 difference? Is that mean difference due simply to sampling error? Our null hypothesis is that the mean difference is 0. Well, we can see that it's not 0, it's minus 5. But is that difference large enough for us to say that it's due to the different methods of accounting, or it's simply due to sampling error? So our alternative hypothesis is that the mean difference does not equal 0. And we're going to be doing two-tailed tests. We'll always do two-tailed tests for this type of test, even though you could do a one-tailed test. We have degrees of freedom. It's the number of pairs of scores minus 1. We have 10 scores, but we have 5 pairs. So our degrees of freedom is going to equal 5 minus 1, which equals 4. We have 4 degrees of freedom. We're going to test this hypothesis at the 0.10 level. And it's a two-tailed test. So what's our critical value? Our critical value, or the t-value that will help us decide whether or not to reject the null hypothesis, our t-critical equals, so if you look at your t-table, for a two-tailed test with 4 degrees of freedom at the 0.1 level of significance, your critical t-value is 2.132. So our decision then will be to reject the null hypothesis if the t-value that we compute is greater than 2.132. And since we're doing a two-tailed test, it doesn't matter whether it's minus or plus. It has to be greater than 2.132. Our formula says to get the t-value, we take the mean difference and we divide it by the standard error of the mean differences. So the hard part now is, how do we compute that standard error of the mean difference? We know what the mean difference is. The mean difference is minus 5. But we have to compute the standard error of the mean difference. To get the standard error of the mean difference, we have to get the standard deviation of the different scores and divide it by the square root of the sample size. How do we get the standard deviation of the different scores? Well, if you go back, so we're going to be dealing now with the difference scores. We have -4, -19. We have 5 difference scores. And you can see those right here. Here are our difference scores. What is the standard deviation of those difference scores? We could use we had a number of formulas for computing standard deviations in Chapter 4. These scores are just like any other score. They're different scores, but it's a single number. To get the standard deviation of the difference scores, we're going to use one of the alternative formulas in Chapter 4. We're going to take the square root of the sum of my squared differences minus the sum of my differences squared divided by n, and I divide that by n minus 1. So we have to square the difference scores and add them up. We have to add up the differences and square it, divide by n, and subtract that value from the square difference scores, divide the numerator by n minus 1, and take the square root of that. Well, we have to square the difference scores. 16, 361, 169, 144, and 9. And if we added up all those difference scores, we would get 600 and 99. So when we add up all these difference scores, 16 plus 361, we get 699. So when we're looking at our formula then, our standard deviation of the differences is going to be 699 minus the sum of my differences squared. The sum of my difference scores is 25. If we square that, we get 625 divided by 5, and all that gets divided by n minus 1, which is 4. If you do that, you will get a standard deviation of the difference scores equal to 11.98. So this equals the standard deviation of the difference scores. To get the standard error of the mean difference, we have to divide that 11.98 by the square root of 5. And if you divide 11.98 by the square root of 5, you will get 5.35. So 11.98 divided by the square root of 5 will give you 5.35. That's how we got the standard error of the mean difference. So now to get our t-value, t is going to equal our mean difference, we're back to our formula here, which is minus 5 divided by 5.35. Which is going to give us a t-value of 0.935. So again, we took our standard deviation of the differences, which is right here. We divided 11.98 by the square root of n, and we got 5.35. And to get our t-value, we took minus 5, which is our mean difference. We're looking at this formula here. And we divided minus 5 by the standard error of the mean difference, 5.35. We got a t-value of 0.935. Our critical t-value is 2.132. Well, this is actually, it's a minus, but it doesn't matter. We have to be greater than 2.132, and we are not. 0.935 is not greater, so we do not reject the null hypothesis. And what we would conclude is there really is no difference in cost between these two types of inventory. In order for us to say that that -5 difference is not due to sampling error, that $5 million less, which last in, last out resulted in, is statistically significant, we had to get a t-value of greater than 2.132, and we did not. So to summarize then, we have two methods of accounting that we're using on 5 products. Each product resulted in a different cost. It was lower for product 1, lower for product 2, higher for product 3, lower for product 4, lower for product 5. The mean difference was $5 million less under the last in, last out method. However, that $5 million is due to sampling error. You would think that, well, $5 million less, that's a lot. It's due to sampling error because we needed a statistic greater than 2.132 to reject the null, and we got 0.935. So in this chapter, remember that we're working with different scores. We have to compute a mean difference. Under the null hypothesis, we're saying that the population mean of different scores equals 0. We compute a sample mean difference, and we want to know whether this sample mean difference is due to sampling error or is it a real difference in the treatments? Is it a real difference? We do a t-test of these mean differences. We compute the mean differences. What difference do we expect? Well, that's our standard deviation, standard error of the mean differences. We have different scores. We compute the standard deviation of the different scores. We divide that by the square root of the sample size, which was 5, to get the standard error of the mean difference. And we have degrees of freedom. We have a critical t-value that we must exceed in order to reject the null. And then we make a decision based on the t-statistic that we computed. In many ways, it follows the same procedures that we learned in Chapter 10. There are differences, though, so it's important to read this chapter carefully so you understand those differences.